welcome back to my channel. So today we continue with the part 3 for the valence bond theory. In this part 3, we will discuss about the octahedral geometry and also the new hybrid orbital of the sp3d2 and also d2 sp3. And yeah, let's start. So for example here, I have the cobalt with 6 fluoride. So first thing is you need to determine the oxidation state of this cobalt. So here this is -6 equals to -3. This is the x, so your x is +3, so the cobalt is +3. And then let's cobalt is +3, 27. Okay, and then the cobalt has 27 atomic number. So this is the Ar4s2 3d7. And then we need to have cobalt 3 plus. So this one will give you Ar3d6. Okay, then let's draw the d orbital. 6. You need to pair. You need to fill up singly and then pair up the electrons. Okay, so what can you see here? We have 4 unpaired electrons, which makes it paramagnetic, and this is what we call high spin complex, because this compound itself, okay, it has 6 fluorine, where the fluorine is actually weak ligand. When you have weak ligand in the compound, we need to consider this one as the high spin complex. And when you have a strong ligand in the complex, it can be considered as the low spin complex. So what happened here? Because we have 6 fluorine here, so you're gonna have, okay, so 6 fluoride. So this is 6 fluoro, okay, in order for you to give hexafluoro. So it will give you 6 times 2 electron, 1 lone pair from each, or 1 lone pair from 1 fluoride. So it will give you 12 electrons. Okay, so here in this case, after the 3D, we have the 4s, 4p, and also the 4d. So this cobalt 3, you need to react with 6 fluoride. So you get this compound, okay, or complex ion here. You get this complex ion. So what happened here? Because it exists as paramagnetic, so you need to start to add on electron from here. You need to add on 12 electron here from the 4s orbital, not from the 3d orbital. Why? Because it is a paramagnetic, and you cannot join, or you cannot add on the electron in here. Okay, if you add on electron in here, they will not become, or this compound will not become a paramagnetic. It will become a diamagnetic compound or complex ion. So you need to start add on this 12 electron from the 4s. So if you add on the 12 electron here from the 4s until the 4d, so this is the 1f. This is the electron from the first f, second, third, fourth, fifth, and also 6th electron. So 6 times 2 will give you 12 electrons. So here, where you have the sp3d2 bonds to the ligand with coordination number of 6. So the structure for this compound is actually cobalt with 6 ligand. So this cobalt is actually surrounded by 6 fluoride here with the charge of 3 minus. So this is a cobaltate. Okay, hexafluorocobaltate 3. Okay, the name for this one is hexafluorocobaltate 3. So if you have a paramagnetic compound with the high spin complex, so in order for you to determine the high spin complex, you need to check the type of ligand. So here we have the weak ligand with where we have the 4 unpaired electron for this cobalt. So it will become the sp3d2 geometry, octahedral. So this is similar example, okay, from the previous one where you have the 6 fluorine here. So the 6 fluorine here, this is the okay, 246, 3d6. I think this is right. Please do correction here. This is not 3d8. It's supposed to be 3d6. Yeah, with no paired electron here and also here. Right, so this is the 3d6. Okay, alright. And then second one, other than sp3d2, we have d2sp3. This is where you have a diamagnetic compound with the low spin complex. So it means that in that compound, it has strong field ligand or strongly ligand. For example, cyanide. So here, this is also a cobalt compound. So cobalt is 27. So here, you need to write down first the electron configuration for the cobalt. This is 3d7. And then you need to check this cobalt. This is cobalt 2 or cobalt 3, the oxidation state here. So this will give you -6 equals to -3. This is X. So the X is +3. So means that you need to have cobalt 3 plus. So this is Ar 3d6, also 3d6. And then you need to have, okay, so then after that, don't forget to draw the d orbital 6. But this one, when you have the cyanide, a strong ligand, they have tendency to form a diamagnetic, as I mentioned before this. And what happened here, they will start to pair up in order to become a diamagnetic instead of paramagnetic. And low spin complex because it has 6 cyanide, strong ligand. So what would you do after that? Okay, here, if you combine all of these electrons and then this cobalt, this is in free ion, and then you add on or you react with 6 cyanide, it will form this compound and they start to pair up the electron. So 6 cyanide will give you 12 electron. 6 cyanide times 2 electron, it will give you 12 electron. So you can start fill up electron from the 3d orbital because you have 2 empty orbital. You need to have empty orbital, only empty orbital. Okay, then start followed by the 4s and also 4p. So you get the d2, this is the d, this is the s, and also this is the p3. So in here, for the octahedral here, this is for d2sp3 diamagnetic and also low spin complex. So the structure for this compound is cobalt with 6 coordination number, Cn, and then you will have 3 minus, so this is a cobaltate. CN and also CN. The name for this compound is hexacyanocobaltate 2. This is hexacyanocobaltate 3. Okay, because this is cobalt 3 plus. Here, other than that, I have example for this chromium. Chromium with 6 ammonia here. Okay, and then what is the atomic number for chromium? Let's find out the atomic number for chromium. Chromium is 24. And first thing, you need to determine the oxidation state for this chromium. So this is 0 equals to positive 3. So the chromium here is positive 3. This one will give you Ar 4s1 3d5. Okay, please remember chromium and copper, they have exception. So you want to have the chromium 3 plus, so this one is Ar. Then you need to remove 3, 1 from here and another 2 from here, so it will give you 3d3. And then here we have 6 ammonia. 6 ammonia will give you 12 electrons. So because here we have 3 unpaired electron with a 2 empty d orbital, you can start add on this 12 electron, start from the 3d. So you can, this is 1 ammonia, 2, 3, 4, 5 and also 6. This is what you get. So you will get D2sp3, right? So in this case, you need to look at the types of the ligand, whether they are strong or weak ligand. If you have strong ligand, usually they will become diamagnetic compound or diamagnetic complex ion. And if you have a weak ligand, usually it will become a paramagnetic compound, right? So yeah, here this is where we can see the difference between the sp3d2 and also d2sp3 hybrids. Okay, actually lies in the principal quantum number of the d orbital. What do you remember about the principal quantum number? This is where you have the number of orbital. Do you still remember the azimuthal principal number, where we have the n equals to 1, 2, 3, 4. This is number of orbital. We have L, M and also S. Do you still remember about this? Four principal quantum number. In this one, we focus in this azimuthal principal number, the number of orbital of the electron or the location of the electron itself. And here for sp3d2, usually the sp and also d orbitals have the same principal quantum number, where usually you can consider this one as a high spin complex. And if you have the d2sp3 hybrids, the principal quantum number of the d orbitals is 1 less than s and also p or orbital. So it will give you a low spin complex. And a complex magnetic properties usually determine which hybrid is being used. So you need to be able to differentiate between the paramagnetic and also the diamagnetic. And then this is the 6 ligand in octahedral crystalline splitting, okay, or crystalline. So it will give you 2 types of hybrid orbital, D2sp3 or sp3d2. This is where we have the same level of orbital, and this is where we have different level of orbital between d, s and also p. And then so we have 6 here, where the coordination number is 6 here, right? Then other than that, this is the 5 orbitals of the 3d, because usually, okay, the d we have 5 here. We have dxy, this is the shape for dxy, and then dyz, dxz, dz squared, and dx squared minus y squared. Right, so this is what I have explained before this in the first class for this semester. Okay, the 5 types of d or orbital. And then this is also the formation example for the formation of D2sp3. What happened here? This is overlapping between orbitals between s, px, py, and pz, and then also the dx2 minus y2 and also dz squared. And then other than that, I have exercise for you to do, and then you need to differentiate or you need to determine the valence bond theory here and determine the hybridization for complex ions here for A until F. So we will discuss this one during our virtual class. I think that's all for today. Thank you everyone, and please don't forget to like, subscribe, and also give comment to my video, and I will see you guys next week. Bye.